What if one of the rarest objects ever discovered entering our solar system did not arrive alone in time? In early July 2025, 3I Atlas was confirmed, the third interstellar visitor ever observed. Almost simultaneously, the most powerful gamma-ray burst on record flashed across our instruments. Same moment, same region of the sky. No clear explanation. Astronomers call these coincidences statistically unlikely. But science begins exactly where easy answers fail, as new data on 3I Atlas continues to arrive in real time. This episode looks at why this alignment is quietly unsettling researchers. Stay with us for the evidence. And if you value careful science, like and subscribe. Now, let's begin. In early July of 2025, astronomers confirmed the detection of a new interstellar visitor now known as 3I Atlas. The object was first identified on July 1st through automated survey systems that continuously scan the sky for faint points of light that shift position against distant stars. These systems are designed to flag objects that move too fast or follow paths that do not match known asteroids or comets. Once 3I Atlas was flagged, observatories around the world began follow-up measurements to determine its speed, direction, and distance. Those early calculations revealed something decisive. The object's trajectory is hyperbolic, meaning it is not gravitationally bound to the Sun. In simple terms, it is moving too fast to be captured. It entered the solar system from interstellar space, passed through, and will leave again without returning. This immediately placed it among the rarest objects ever observed. Before this, only 2 interstellar objects had been confirmed with certainty, making 3I Atlas the third of its kind. Further refinement of the orbit showed another notable feature. Its path is closely aligned with the ecliptic plane, the flat region of space in which Earth and the other major planets orbit. Most interstellar objects could arrive from any direction, so this alignment is not required by chance alone. While alignment does not imply purpose, it does influence how the object interacts with planetary environments and the solar wind as it travels inward. As it moves through the inner solar system, 3I Atlas passes relatively close to Mars and later approaches Jupiter for a fast flyby scheduled for March of 2026. Jupiter's gravity is strong enough to reshape the orbits of comets, asteroids, and debris throughout the solar system. In this case, however, the object's speed is so high that even Jupiter cannot capture it. Instead, Jupiter briefly alters its direction before it continues outward toward interstellar space. This short but intense interaction provides scientists with a rare chance to observe how an interstellar object responds to extreme gravitational and electromagnetic conditions. As observations continued, researchers began to notice behaviors that did not match expectations based on well-studied comets. One of the earliest visual clues involved the structure and orientation of the object's tail. In typical comets, tails form as sunlight heats surface material, causing gas and dust to stream away from the nucleus. Solar radiation pressure and the solar wind then push this material directly away from the Sun. In the case of 3I Atlas, the observed tail does not consistently follow that pattern. Its orientation appears offset, pointing downward relative to its direction of motion rather than directly away from the Sun. This unusual geometry suggests that forces other than simple dust release may be shaping the surrounding material. Such forces often involve charged particles and magnetic fields rather than gravity alone. This interpretation gained support as additional measurements revealed changes in the object's visible color over time. Early observations showed emissions dominated by red wavelengths. As the object progressed along its path, those emissions shifted toward green. In comet science, color changes are usually linked to specific gases becoming excited by sunlight. Different molecules glow at different wavelengths when energized. However, the timing and scale of the color shift observed in 3I Atlas do not align cleanly with standard models. The change suggests that the composition of the surrounding cloud, or the way it interacts with energy from the sun, may be more complex than expected for a typical icy body. Plasma interactions offer a possible framework for understanding several of these observations. Plasma is a state of matter in which electrons are separated from atoms, allowing electric and magnetic fields to dominate behavior. Much of space within the solar system exists in this plasma state, especially near the sun, where charged particles flow outward as the solar wind. Objects moving through this environment can generate electrical currents, magnetic disturbances, and structured flows of charged material. Evidence suggests that 3I Atlas is not merely releasing neutral gas and dust, but is actively interacting with surrounding plasma. This can produce tail structures shaped by magnetic field lines rather than by radiation pressure alone. Such interactions are dynamic and can change rapidly as solar conditions vary. These effects became more pronounced during periods of increased solar activity. From late October through the object's closest approach to the sun near the end of that month, instruments recorded changes in brightness, emission structure, and plasma behavior that coincided with elevated solar flare activity. Similar responses were detected again in the days that followed. This pattern does not imply control or intent. It reflects the sensitivity of plasma systems to changes in the sun's electromagnetic output. Taken together, these observations explain why 3I Atlas has drawn sustained scientific attention. Researchers have explored multiple interpretations, including whether it should be classified as an interstellar comet or as a broader category of interstellar object that does not fit neatly into existing labels. At this stage, conclusions remain grounded in measurement rather than speculation. What is clear is that models developed primarily from solar system bodies may not fully describe objects formed in very different stellar environments. One method scientists use to investigate rare phenomena is the study of timing, when independent events align closely in time or direction. They warrant careful examination. This does not mean coincidence implies causation. It means that extreme alignments sometimes reveal gaps in understanding. In the case of 3I Atlas, such a temporal alignment occurred almost immediately after its discovery, less than 24 hours after the object was first confirmed. Detectors across multiple observatories recorded an extraordinary gamma-ray burst. Gamma rays are the highest energy form of electromagnetic radiation. Each gamma-ray photon carries far more energy than photons of visible light, and bursts of gamma rays represent the most powerful explosions known in the universe. Gamma-ray bursts originate far beyond the solar system, often at distances measured in billions of light-years. Despite their remoteness, their signals are intense enough to be detected by instruments orbiting Earth and by space-based observatories. These events briefly bathe detectors in high-energy radiation from a precise location in the sky. The exact origins of gamma-ray bursts are still not fully understood. Some models associate them with massive stars collapsing into black holes. Others involve the merger of neutron stars or extreme gravitational disruptions in distant galaxies. Each model explains certain features, but none accounts for all observed behavior. What scientists agree on is that gamma-ray bursts are rare, short-lived, and extraordinarily energetic. The event recorded on July 2nd of 2025 did not follow typical patterns. Instead of lasting seconds or minutes, the burst continued for more than 24 hours. Within that extended duration, instruments identified 3 distinct pulses of intense emission spread across approximately 7 hours. Each pulse rose sharply, released enormous energy, and then subsided before the next began. For context, most gamma-ray bursts end before a single minute passes. A small number extend into tens of minutes, and only a handful have lasted longer than an hour. The July 2nd event exceeded all previous records by a wide margin, making it the longest gamma-ray burst ever observed by a significant difference. The gamma-ray burst detected on July 2nd of 2025 stands out not only for its duration, but also for its intensity. In terms of measured brightness and total energy, it ranks as the second strongest gamma-ray burst ever recorded. The strongest event occurred on October 9th of 2022. An explosion so powerful that astronomers informally labeled it the biggest of all time. That earlier event was described as a 1 in 10,000 year occurrence, based on how rarely bursts of that strength appear in observational records. The July 2nd burst now follows closely behind it. It was the second brightest, the second strongest by energy output, and the longest-lasting gamma-ray burst ever observed. Its signal persisted for more than 24 hours and was marked by 3 distinct pulses. Each pulse rose sharply above background levels, released a vast amount of energy, and then declined before the next began. The final pulse was the strongest of the 3. In astronomical data, a pulse refers to a concentrated release of radiation that stands out clearly from surrounding noise. Multiple pulses within a single gamma-ray burst are not unheard of, but they are usually compressed into short time spans. In this case, the pulses were separated by hours and followed a clear temporal pattern. The emission did not appear chaotic or random. Instead, it unfolded with a steady rhythm, suggesting an underlying physical process that evolved over time rather than collapsing all at once. At the same time, 3I Atlas had just been confirmed as the third interstellar object ever observed passing through the solar system. The numerical coincidence is easy to notice, but the scientific relevance lies elsewhere. These are entirely different types of phenomena. One is a small object moving through the Sun's gravitational domain at a speed of roughly 60 kilometers per second, slightly faster as it approaches perihelion. The other is a flash of radiation released by a catastrophic event that occurred billions of years ago in a distant galaxy. Based on its measured velocity, 3I Atlas cannot have originated from the same region of space as the gamma-ray burst. An object traveling at tens of kilometers per second would require timescales far longer than the age of the universe to cross distances measured in billions of light years. The gamma rays detected on July 2nd began their journey toward Earth roughly 5 billion years ago, long before the solar system existed in its current form. The two events are not connected by any physical mechanism that could link cause and effect. What draws attention is the timing and geometry of observation. The gamma-ray burst arrived at Earth less than 24 hours after 3I Atlas was first detected. In addition, both signals came from nearly the same region of the sky when mapped from Earth's point of view. 3I Atlas approached from the direction of the constellation Sagittarius. The gamma-ray burst was recorded from a location just above that same constellation, separated by a small angle on the sky. It is important to clarify what this means. Constellations are patterns projected onto the celestial sphere, not physical regions of space. Objects that appear close together in a constellation can be separated by vast distances. The alignment here refers to viewing direction, not shared origin. Still, astronomers pay close attention when rare events coincide closely in both time and apparent position, because such alignments are statistically uncommon within limited observation windows. At present, the age of 3I Atlas remains unknown. It could be millions or billions of years old, shaped by environments far different from the solar system. Its arrival now, during an era of sensitive instruments capable of detecting subtle electromagnetic signals, is a matter of timing rather than design. The gamma-ray burst, by contrast, represents a distant past event finally reaching Earth. The overlap exists only at the moment of detection, when light from one phenomenon and matter from another intersect our instruments at the same time. While these observations raise questions, they do not yet offer answers. From a scientific standpoint, the correct response is not to assign meaning, but to examine data carefully and separate coincidence from mechanism. That approach becomes especially important when discussing new observations of 3I Atlas itself. Recent imaging has provided additional insight into the object's physical behavior. Observations in the X-ray portion of the electromagnetic spectrum were carried out using the XMM Newton Space Telescope operated by the European Space Agency. These observations were conducted on December 3rd and involved roughly 20 hours of continuous exposure. X-ray imaging allows astronomers to study processes that are invisible in ordinary light, especially those involving ionized gas. Unlike gamma rays, which are produced only by extremely energetic cosmic events, X-rays can be generated locally within the solar system. When neutral gas released by a comet or interstellar object interacts with the solar wind, atoms can lose electrons in a process called ionization. As electrons rearrange or recombine, they can emit soft X-ray photons. This creates a faint but measurable glow around the object. In the X-ray images of 3I Atlas, a denser central region of emission is visible, corresponding to the inner coma where gas production is highest. Beyond that, a more diffuse halo extends outward, tracing the interaction between the object's released material and the surrounding plasma environment. This emission does not indicate internal power generation. It reflects the object's response to external energy supplied by the sun and the solar wind. Diffuse X-ray light is also observed throughout interplanetary space. Interstellar gas entering the solar system becomes ionized and contributes to a background glow. Earth passes through regions of enhanced interstellar gas flow each year during late December and January, and instruments often record a general increase in soft X-ray emission during that period. The X-ray signature of 3I Atlas appears superimposed on this broader environment, standing out because of its localized structure. These observations confirm that 3I Atlas is actively interacting with its surroundings as it moves through the solar system. The object reflects and emits X-rays as a consequence of gas release, ionization, and electromagnetic interaction. This behavior fits within known plasma physics, even if the specific details differ from familiar comets. Taken together, the picture that emerges is one of convergence in observation rather than connection in origin. 3I Atlas entered the solar system and was detected for the first time. Within a day, Earth received radiation from one of the most powerful and longest gamma-ray bursts ever recorded, originating billions of light-years away. The two events are unrelated in space and time, yet they intersected our instruments almost simultaneously. As 3I Atlas continues its passage and as data from high-energy observatories are analyzed further, the focus remains on measurement and comparison. The coincidence marks a moment where multiple extremes of the universe briefly overlapped in human observation, without implying shared cause or deeper linkage beyond that convergence. To understand why GRB250702b drew such intense attention, it helps to begin with duration. Gamma-ray bursts are usually identified by sharp spikes of radiation that rise quickly and fade just as fast. In most cases, the entire event is over in seconds, sometimes stretching to a minute. When scientists plot these events, they use a graph that shows brightness on the vertical axis and time on the horizontal axis. For a typical gamma-ray burst, that horizontal scale often spans about 60 seconds. Within that short window, a single narrow peak appears and then disappears. GRB250702b looked nothing like that. When astronomers examined its light curve, the time axis extended not for seconds or minutes, but for hours. Observations continued for roughly 8 hours during the most active phase, and weaker emission persisted far longer. Instead of a single spike, the graph showed sustained activity that continued to release energy long after a normal burst would have ended. This matters because total energy is not determined by brightness alone. It depends on how long the source continues to emit radiation. A brief flash can be intense, but an event that remains active for hours releases far more energy overall. One simple way to think about this is to imagine the area under the brightness curve, even without using equations. The idea is clear. A strong signal lasting 1 minute contains far less total energy than a slightly weaker signal that continues for many hours. In the case of GRB250702b, both brightness and duration were extreme. As the data accumulated, researchers identified 3 distinct phases of emission within the broader event. These are referred to as pulses. Each pulse represents a period when the source released gamma rays at a much higher rate than the surrounding intervals. The first pulse rose sharply and then declined. After a quieter period, a second pulse followed, again rising above background levels. The third and final pulse was the strongest of all, reaching higher intensity than the first 2 before fading away. In gamma-ray astronomy, pulses are understood as stages in a physical process rather than separate events. Many bursts show complex internal structure, especially when the central engine continues to inject energy over time. What made this case unusual was the spacing. The pulses were separated by long intervals measured in hours, not seconds. Despite that spacing, they followed a clear progression rather than appearing randomly scattered. At first, this structure caused confusion. Automated detection systems are designed to flag sudden increases in gamma-ray counts. When separate pulses arrive hours apart, the software can interpret them as independent bursts. That is why the event initially received multiple designations, including suffixes such as B, D, and E. Each label corresponded to a detected spike in radiation. As more data were analyzed, scientists compared the precise sky positions associated with each detection. When those positions were mapped, it became clear that the pulses all originated from the same location on the celestial sphere. Their directional overlap was far tighter than would be expected by chance. This confirmed that the signals did not come from separate sources. Instead, they were different phases of one exceptionally long and powerful gamma-ray burst. During the same time frame, another gamma-ray burst was detected and labeled with a different suffix. That event arrived close in time, but from a clearly different region of the sky. Its direction, estimated distance, and other properties did not match the long-duration event. By separating that unrelated burst from the main signal, researchers reinforced the conclusion that GRB250702b was a single, coherent phenomenon rather than a cluster of unrelated explosions. This careful separation is a routine part of high-energy astronomy. The sky is constantly monitored, and overlapping events can occur by chance. Scientists rely on position, timing, and spectral properties to decide which signals belong together and which do not. In this case, the evidence strongly supported a single source producing multiple pulses over an extended period. Another unusual feature appeared when scientists examined data outside the gamma-ray range. X-ray instruments recorded elevated emission from the same direction up to a day before the final and strongest gamma-ray pulse. Normally, gamma-ray detectors are triggered by an initial burst, and the event concludes quickly. Seeing X-rays first, followed by delayed gamma-ray activity, is rare but not without precedent. These early X-rays are often referred to as precursor emission. They suggest that the system producing the burst was already active before the most violent phase began. In some models, this can happen when matter begins to interact or collapse in stages, gradually building toward a final release of energy. The key point is that such behavior reflects complex astrophysical processes rather than a single instantaneous explosion. The timing of this precursor activity overlapped closely with the period when astronomers were confirming the discovery of 3I Atlas. From a scientific perspective, this overlap is noted as a coincidence in observation. The gamma rays and X-rays originated far beyond the solar system, while 3I Atlas is a local interstellar object passing through the Sun's environment. There is no physical mechanism that links the two. The connection exists only in the moment their signals reached Earth and were recorded by instruments. To better understand the gamma-ray burst itself, astronomers work to refine its position on the sky. Initial detections provide approximate locations, but follow-up observations can narrow these down significantly. By combining data from multiple detectors, scientists produced a more precise focus map of the source region. This refinement allowed ground-based and space-based telescopes to target the area for deeper study. Observatories such as Gemini and the James Webb Space Telescope were used to examine the region associated with the burst. These instruments do not detect gamma rays directly. Instead, they search for afterglow emission at longer wavelengths, such as infrared and visible light. Afterglows can reveal information about the environment around the source, including the type of galaxy in which it occurred and the conditions of the surrounding material. The refined map showed that the three major pulses all aligned with the same compact region. This consistency further confirmed that GRB250702b was a single prolonged event. The additional observations did not change its classification as the longest duration gamma-ray burst ever recorded and the second strongest by measured energy output. By the time these analyses were complete, the picture had become clear. GRB250702b was an extreme example of a phenomenon that is already among the most energetic known in the universe. Its extended duration, structured pulses, and precursor X-ray emission placed it well outside the typical range of gamma-ray bursts. At the same time, its properties fit within the broader framework of high-energy astrophysics, where rare events occasionally push beyond established expectations. These findings provided a detailed foundation for further study of the burst's origin and mechanisms. They also established a precise observational context for its timing relative to other astronomical discoveries made during the same period, including the arrival of 3I Atlas into the inner solar system. When astronomers examined the sky position of GRB250702b, one of the first points of reference was the broader structure of the Milky Way. From Earth's perspective, the burst appeared along the same general band of sky that traces the plane of our galaxy, near the direction of the galactic center. This region is densely populated in projection, meaning many distant objects appear close together on the sky, even though they are separated by immense physical distances. Seeing multiple extreme events aligned along this band is not unexpected, but it does require careful analysis to separate appearance from physical connection. Initial gamma-ray detections provide only rough locations. To identify the source more precisely, astronomers rely on follow-up observations at other wavelengths. Ground-based telescopes, such as Gemini, were used first to narrow down the region of interest. These optical observations reduced the uncertainty area and revealed a faint host galaxy at the burst location. However, because the source is extremely distant, much of its light is stretched to longer wavelengths by cosmic expansion. This is where infrared observations become essential. The James Webb Space Telescope, with its high sensitivity in the infrared, was able to image the host galaxy much more clearly. In these observations, the galaxy appears as a compact, distant system whose light has traveled for billions of years before reaching Earth. Based on spectral measurements and modeling, the current estimate places the galaxy at an age of approximately 4.9 billion years, with an uncertainty of about 0.6 of a billion years. This places the explosion deep in cosmic history, long before the solar system formed. When light travels across such distances, it carries information from the past. The photons detected from GRB250702b were emitted billions of years ago and have been moving through space at a constant speed ever since. When they arrived at Earth in early July of 2025, they did not signal a recent event in that distant galaxy. They marked the moment when ancient radiation finally intersected with modern instruments. The overlap in time with the detection of 3I Atlas reflects the timing of observation, not the timing of origin. To understand the full scope of this event, astronomers assembled data from across the electromagnetic spectrum. Gamma-ray detectors recorded the initial high-energy emission. X-ray observatories tracked both precursor activity and the evolving afterglow. Optical telescopes captured fading visible light. Infrared instruments, including James Webb, revealed the host galaxy and its environment. Radio telescopes monitored long wavelength emission that persisted long after the initial burst. This broad coverage confirmed that GRB250702b was not only intense in gamma rays, but energetic across all measurable wavelengths. Such wide spectrum emission is expected for powerful cosmic explosions. The highest energy radiation, gamma rays and X-rays, typically appears first and fades quickly. Lower energy emissions, such as optical and radio waves, often last much longer. In this case, radio observations continued for weeks and months after the initial detection and remain ongoing. These long-lived signals help scientists study how the explosion interacts with surrounding material as it expands outward. Detailed analysis of the timing revealed several features that set this burst apart. As established earlier, it was unprecedented in duration, extending far beyond any previously recorded gamma-ray burst. Its internal structure consisted of 3 clearly separated pulses, each representing a major release of energy. The final pulse was the strongest, a pattern that is uncommon in known bursts. In addition, X-ray emission was detected roughly 1 day before the strongest gamma-ray activity, indicating that the system was active well before the main energy release. The timing of these components has been measured with high precision. The interval between the first and second major pulses was approximately 2,825 seconds. The third pulse occurred after a further interval that closely matched an integer multiple of that same duration, differing by only a few seconds. From a scientific standpoint, this regular spacing is described as orderly rather than random. It suggests that the source released energy in stages governed by an internal physical process, rather than in a single uncontrolled collapse. Orderly timing does not imply intention or signaling. In astrophysics, structured behavior often emerges from natural systems. Rotating objects, accretion flows, and magnetic instabilities can all produce repeated or staged emissions. What makes GRB250702b unusual is not that it shows structure, but that the structure unfolds over such long time scales and with such extreme energy. Throughout this period, astronomers were also confirming the nature of 3I Atlas as an interstellar object. That object, moving through the solar system at tens of kilometers per second, is governed by local gravitational and electromagnetic conditions. The gamma-ray burst, by contrast, reflects processes occurring in a distant galaxy billions of years ago. The two phenomena are separated by vast differences in scale, distance, and origin. What connects them is the moment of detection. Instruments on and around Earth recorded the arrival of ancient radiation from a distant explosion at nearly the same time that telescopes identified a rare interstellar visitor passing through the solar system. From a scientific perspective, this convergence highlights the breadth of modern observation. It shows how events from the deepest past of the universe and objects moving through our immediate cosmic neighborhood can enter human awareness at the same time. The significance of GRB250702b lies in its physical properties rather than any implied message. Its unprecedented duration, structured pulse sequence, early X-ray activity, and broad spectral emission challenge existing models of gamma-ray bursts. Each of these features provides constraints that theorists must account for when refining explanations of how such explosions occur. By anchoring the burst to a specific host galaxy and tracking its emissions across multiple wavelengths, astronomers have established a solid observational framework. This framework allows further analysis of the mechanisms capable of sustaining energy release over many hours and producing repeated pulses without exhausting the system. It also provides a clear reference point in time for comparing other astronomical discoveries made during the same observational window. In this way, GRB250702b stands as a benchmark event. It represents an extreme but measurable outcome of known physical processes operating under conditions rarely encountered. Its coincidence in detection time with the arrival of 3I Atlas underscores not a hidden connection, but the expanding reach of observation, where distant cosmic history and local interstellar motion are recorded side by side within the same narrow slice of time. When researchers return to the time-resolved data for GRB250702b, one feature continued to stand out: the structure of the emission over time. In a typical gamma-ray burst, the recorded signal rises sharply and then fades away, often within seconds. Even when multiple peaks appear, they are usually crowded together, forming a jagged cluster rather than a clearly separated sequence. In this case, however, the strongest phases of emission were spaced apart in a regular way. The light curve shows 3 dominant peaks separated by long intervals. When those intervals are measured precisely, they are found to be similar in scale rather than random. This kind of regular temporal spacing is described in astrophysics as structured or ordered. It does not imply intention or communication. Instead, it suggests that the physical system producing the burst released energy in stages, governed by an internal process that unfolded over time. Such behavior is not unknown in high-energy astronomy, but it is uncommon at this scale. Processes involving rotating compact objects, unstable magnetic fields, or prolonged accretion can sometimes produce repeated outbursts. What makes GRB250702b unusual is that these stages occurred over hours rather than seconds, while still maintaining clear separation and a consistent progression in strength, with the final pulse being the most energetic. From a scientific perspective, this kind of structure draws attention because it places constraints on theoretical models. Any explanation for the burst must account not only for the total energy released, but also for how that energy was delivered over time. Models that assume a single, brief collapse struggle to reproduce such extended and organized emission. Models involving sustained activity or repeated instabilities are more promising. But even these are being tested by the extreme duration observed here. At the same time these data were being analyzed, the discovery of 3I Atlas was still fresh. The interstellar object had been identified only hours earlier, and its trajectory and basic properties were still under review. The coincidence in detection time naturally led to comparisons. But the scientific task was to examine geometry and timing carefully rather than draw conclusions based on impression. To do this, astronomers relied on standard celestial coordinate systems that allow positions to be compared accurately. Every object on the sky can be assigned a right ascension and declination, much like longitude and latitude on Earth. Using these coordinates, the apparent position of GRB250702b at the time of its strongest emission was plotted on a sky map. The same was done for 3I Atlas at corresponding times. When these positions are compared, they are found to lie close together in angular terms. That is, from Earth's point of view, they appear in nearly the same direction against the background of stars. The separation is small on the sky, placing both near the region associated with the constellation Sagittarius. This region coincides with the plane of the Milky Way, where the density of stars, gas, and distant galaxies is highest in projection. It is essential to clarify what this alignment means and what it does not mean. Angular proximity on the sky does not imply physical proximity in space. GRB250702b originated in a galaxy billions of light-years away. 3I Atlas is moving through the solar system at a distance measured in astronomical units. The two are separated by an enormous gulf of space and have entirely different origins. However, angular alignment combined with close timing is still noteworthy from an observational standpoint. When two rare events appear from nearly the same direction within a narrow time window, astronomers take note, not as evidence of connection, but as an uncommon overlap in observation. Modern surveys monitor vast portions of the sky continuously. Yet the number of extreme events within any given day remains small. Overlaps of this kind are therefore infrequent. To confirm the positions involved, astronomers did not rely on a single instrument. The gamma-ray burst location was refined using data from multiple detectors sensitive to high-energy radiation. These provided an initial error region. That region was then narrowed through follow-up observations at longer wavelengths, including X-ray, optical, and infrared. Each step reduced uncertainty and improved confidence in the source position. 3I Atlas, meanwhile, was tracked using astrometric measurements that map its motion against background stars. By tracing its path backward in time, researchers could identify the direction from which it entered the solar system. These reconstructions showed that the object approached from the same general region of the sky near Sagittarius before moving inward toward the plane of the planets. When both datasets are placed on the same coordinate framework, the overlap becomes clear. The gamma-ray burst source and the incoming path of the interstellar object occupy nearby directions on the celestial sphere. The proximity is angular rather than physical, but it is precise enough to rule out vague or approximate alignment. This is a measured result based on standard coordinate comparisons. At this point, scientific caution becomes especially important. Human perception is highly sensitive to patterns, especially when dealing with rare and striking events. Recognizing a pattern does not mean that the pattern reflects an underlying causal link. In astronomy, many alignments occur simply because the sky is observed from a fixed vantage point and because certain regions, such as the galactic plane, contain more sources than others. The appropriate response is therefore to document the alignment accurately, note its rarity, and then return to physical explanations grounded in known processes. In this case, there is no mechanism by which a gamma-ray burst occurring billions of years ago could influence the arrival of an interstellar object in the present day, or vice versa. Their timelines and physical scales do not intersect in that way. What can be said is that both events were recorded by the same generation of instruments within the same short period of time. This reflects the reach of modern astronomy. Sensitive detectors now monitor the entire electromagnetic spectrum, from gamma rays to radio waves, while wide-field surveys track small bodies moving through the solar system. As a result, events from vastly different domains can enter the scientific record side by side. The regular structure seen in the gamma-ray burst reinforces this point. Its ordered sequence of pulses indicates a complex astrophysical process that unfolded long before Earth existed. The structured timing challenges current models and provides valuable data for refining them. At the same time, the arrival of 3I Atlas offers a rare opportunity to study material formed around another star system as it passes through our own. Each phenomenon stands on its own scientifically. The gamma-ray burst informs models of extreme energy release in distant galaxies. The interstellar object informs models of planetary system formation and the distribution of material between stars. Their overlap in detection time and sky position does not merge these topics, but it does place them within the same observational context by carefully separating what is measured from what is inferred. Researchers maintain clarity. The data show an unusual gamma-ray burst with extended structured emission. The data also show an interstellar object entering the solar system from a nearby direction on the sky. Both findings are robust. Any further interpretation must remain consistent with physical constraints and observational evidence. Seen this way, the moment is notable not because it suggests hidden meaning, but because it highlights how much of the universe can now be observed at once. Ancient radiation from a distant galaxy and a small object passing close to home were recorded almost simultaneously, each revealing different aspects of cosmic behavior. The convergence lies in observation, not in origin. And it underscores the expanding scope of what astronomy is now able to detect and measure. As the observational picture expanded, attention naturally shifted toward the broader geometric context in which these events were being recorded. When astronomers speak about alignments in the solar system, they are not describing planets lining up physically in space like beads on a string. They are describing how objects appear from a single viewpoint on Earth, projected onto the celestial sphere. This distinction matters. Alignment, in this sense, is about perspective and geometry, not about proximity or interaction. All major planets orbit the Sun in roughly the same flat structure, a remnant of the rotating disk of gas and dust from which the solar system formed. Because these orbital planes are only slightly tilted relative to one another, planets often appear along similar arcs of the sky when viewed from Earth. As each planet moves at its own pace, there are periods when several of them occupy a narrow angular region at the same time. These groupings are predictable, repeatable, and well understood within orbital mechanics. In the period leading into early January, calculations show such a temporary configuration taking shape. Mars, Venus, Mercury, Earth, and Jupiter all appear near the same general plane when projected onto the sky. From Earth's viewpoint, this grouping tightens over a few days in early January, when their apparent angular separation reaches a minimum. Before and after that point, the configuration is looser, but still recognizable. This kind of clustering is not rare. Similar arrangements occur regularly as part of the normal rhythm of planetary motion. Because these events are easy to visualize, they are often illustrated with diagrams or simulations. It is essential to understand the limits of those representations. The planets are never drawn to scale. If they were, the distances between them would be so large that the planets themselves would be nearly invisible. To make geometry visible on a screen, distances are compressed and angles are exaggerated. The apparent closeness in such images reflects alignment on the sky, not actual closeness in space. This distinction helps avoid a common misunderstanding. Planetary alignments do not create new gravitational effects or sudden changes in force. The gravitational pull between planets depends on their true distances, not on how they appear from Earth. During an alignment, those distances remain essentially unchanged. The same orbital laws apply, and the planets continue along their paths without disruption. Within this early January configuration, Earth and Jupiter appear aligned toward the region of the sky associated with the constellation Gemini. On the opposite side of the sky, nearly 180 degrees away along the same great circle, lie constellations associated with Sagittarius and nearby star fields that trace the plane of the Milky Way. This opposition is a basic feature of spherical geometry. directions separated by 180 degrees, are opposite lines of sight from the observer's position. Constellations themselves are not physical structures. They are patterns defined by human convention, grouping stars that appear close together on the sky but may be separated by vast distances. Sagittarius, however, serves as a useful marker because it points roughly toward the dense central region of the Milky Way. Along this direction, the line of sight passes through thick layers of stars, gas, dust, and distant galaxies. As a result, many unrelated astronomical phenomena are observed against this same background. This is why gamma-ray bursts, distant galaxies, and interstellar objects can all appear projected near Sagittarius without sharing any physical connection. The region is crowded in projection, not because objects are interacting, but because the geometry of our galaxy places more material along that line of sight. From Earth, the sky in that direction simply contains more sources layered at different distances. When the incoming trajectory of 3I Atlas is reconstructed using astrometric measurements, it points back toward this same general region of the sky. This reflects the direction from which the object entered the solar system, not a destination or origin point within the galaxy. Interstellar objects can arrive from many directions, but statistically, more are expected to appear near the galactic plane simply because that plane contains more stars and more planetary systems capable of ejecting material into interstellar space. At the same time, GRB250702b was localized to a distant host galaxy that also appears near this region when mapped onto the sky. The gamma-ray burst originated billions of light-years away, far beyond the Milky Way. Yet its apparent position falls within the same broad background of stars and dust. The similarity lies entirely in viewing direction. The distances involved differ by orders of magnitude, and there is no overlap in physical space. The planetary configuration in early January does not influence either phenomenon. The motion of 3I Atlas through the solar system is governed by its velocity and by gravitational forces from the Sun and planets, with Jupiter providing the most significant perturbation. These forces are calculable and have been modeled precisely. The gamma-ray burst radiation, meanwhile, completed its journey long before the planets reached their current positions. By the time Earth detected those photons, the event that produced them was already ancient history. What makes this situation noteworthy is not interaction, but coincidence in observation. Within a relatively short span of time, astronomers recorded a rare interstellar object passing through the solar system, one of the most extreme gamma-ray bursts ever measured, and a recognizable geometric clustering of planets along the same general plane of the sky. Each phenomenon is well understood within its own scientific framework. Their concurrence highlights the density of information captured during a narrow observational window. It is important to separate coincidence from causation. In physics, resonance describes a specific interaction in which systems exchange energy efficiently due to matching frequencies or conditions. No such mechanism exists between planetary alignments, gamma-ray bursts, and interstellar objects. The alignment of planets is a visual configuration. The gamma-ray burst is a distant explosion whose detectable effect at Earth is limited to brief radiation. 3I Atlas is a solid body moving under gravitational control. These processes operate independently. Scientific analysis relies on separating variables rather than combining them. Orbital mechanics is used to describe the motion of planets and small bodies. High-energy astrophysics addresses gamma-ray bursts and their afterglows. Observational geometry provides the framework for comparing directions on the sky. When each phenomenon is analyzed within its proper domain, the overall picture remains coherent and consistent with known laws of physics. The feeling that something is happening often arises when multiple rare events occur close together in time. Human cognition is highly sensitive to pattern recognition, especially when events are unusual or visually striking. Science accounts for this tendency by relying on measurement, statistics, and modeling rather than intuition. In this case, the measurements confirm a close overlap in timing and apparent direction, but they do not indicate a shared cause or interaction. What the data do reveal is the expanding reach of modern astronomy. Instruments now monitor the sky continuously across the electromagnetic spectrum. Gamma-ray detectors scan for brief flashes of high-energy radiation, X-ray, optical, infrared, and radio telescopes follow up to capture afterglows and host environments. At the same time, wide-field surveys track faint-moving objects within the solar system, identifying interstellar visitors earlier and more reliably than ever before. Planetary motions, once charted with pen and paper, can now be simulated with high precision years or decades in advance. These tools make it easy to visualize configurations that would once have gone unnoticed. As observational coverage increases, overlaps between unrelated phenomena become more visible. Not because the universe has changed, but because our ability to observe it has improved. For 3I Atlas, ongoing study focuses on its physical properties, its interaction with the solar wind, and what its composition reveals about material formed around another star. For GRB250702b, attention centers on its unprecedented duration, its structured emission, and the constraints it places on models of extreme cosmic explosions. Planetary alignments serve as a familiar geometric backdrop that helps orient observations, but they do not drive or influence these events. Taken together, these elements form a snapshot of astronomical activity during a narrow slice of time. The snapshot is dense with information because modern instruments capture more data across more domains than ever before. The significance lies in what can be measured and learned from each phenomenon individually, rather than in any implied connection between them. By maintaining clear boundaries between observation, interpretation, and physical causation, the narrative remains grounded in evidence. The convergence of observation highlights the scope of contemporary science, not a convergence of forces or intentions. Each phenomenon continues along its own path, governed by well-tested laws, contributing its own piece to the broader understanding of how the universe operates across vastly different scales.